So, hi, Ritika, it's Traxler. I'm hoping to somehow tie all of the Lewis structure stuff together. So, the idea behind the Lewis structure is that the structure of a covalently bonded molecule helps you understand the properties of that molecule, like whether it will dissolve in water, if whether it's polar or non-polar, um, the uh, give you a feel for the strength of the intermolecular forces between them and what those intermolecular forces are. So the big idea behind Lewis structure is that electrons around a central atom are always paired. They could be lone pairs of unbonded electrons, or they could be pairs of electrons bonded with another atom. And we call this valence shell electron pair repulsion theory. Oh, I know, VSEPR. And the idea is that pairs of electrons will always arrange themselves as far apart from each other as they can. So the idea, I think, to take the visual out of it, the idea is to just directly relate the structure of the molecule to a shape, to a hybridization, to a geometry. Those are the things that you're expected to know for the class and for the AP test. So let's say you have a chemical like methane. It has the formula CH4. And the idea is you think of the first atom, the carbon, as being the central atom, and therefore it's going to bond to the hydrogens. So whatever atoms that you have in a given molecule, they have to be bonded together. And in the case of a Lewis structure, they have to be bonded together covalently. So the only way that the carbon can hook up with four hydrogens is to make a single bond with each of the four hydrogens. So the steps in the Lewis structure are to one, count the number of valence electrons. So carbon's in column four, it has four. Hydrogen only has one valence electron, and there's four of them. So that's the four valence electrons from the carbon and four from the four hydrogens, or 8 electrons. Cool. Step two is to make a single bond between the carbon and each of the four hydrogens. Well, that's going to use up all 8 of those electrons. 4 bonds, 2 electrons in each, 8 total electrons. So now you have a carbon with 4 single bonds. What's the farthest apart 4 single bonds can get? Well, the farthest apart 4 single bonds can get would lead you to a tetrahedral shape. And I think that's the part that you have to remember. If you have 4 areas of space occupied with electrons, either as bonds or unbonded pairs, then you're going to get a tetrahedral shape. The tetrahedral shape has the electrons at an angle of 109.5 degrees. It means that you must have, since you have 4 areas of space occupied, you have to have 4 orbitals. And so you always have one s and you have up to 3 p's. So that's one s and 3 p's is 4 orbitals. So that's sp3 hybridized. Cool. And that's kind of the whole thing all crammed into one space. That if you know how many areas of space are around the electron, then you know all of those things. You know its geometry, tetrahedral, you know its angle, 109.5, and you know its hybridization, sp3. Cool. Now, where the wrinkles come in, and by the way, tetrahedral is always going to be the most likely shape and arrangement because everything wants a full shell, which we think of as 8 electrons, and therefore 4 areas of space. Now, where things get weird is whether those areas of space are occupied or not. So if you have something like NH3, ammonia, well, you also have 8 electrons. When you put N in the center and you make 3 bonds, 2 electrons each, you've only used up 6 of the 8 electrons. So those other 2 have to go somewhere. So now you have an unbound pair on that nitrogen. So in some respects, it still is the same, has the same everything as the methane. There's still 4 areas of space occupied with electrons. We would still say its electron arrangement is tetrahedral. We would still say that the bond angle is 109.5 and the hybridization is sp3. But this time we only have 3 bonds. So if you only have 3 bonded pairs of electrons, then when we try and talk about the areas of space, we further define it as the areas of space occupied by bonds. And now you only have 3 areas of space occupied by bonds. And so we would say the geometry of this is trigonal pyramidal. If we drew it, the three uh, the 3 areas of space occupied with electrons would create this little flat pyramid, hence the name. Okay, and I know that doesn't feel very good, but again, we have to differentiate between bonded pairs of electrons and the total number of electrons. So when you talk about water, again, you've got 8 electrons. So again, it's going to be tetrahedral, the angle, the hybridization, all are the same as the ammonia or the methane, but there's only 2 areas of space occupied by bonds. And so it would be bent or V-shaped by, um, by geometry and tetrahedral by electron arrangement. If you had something like hydrogen fluoride, HF, now you only have 1 bond, and so it would be linear. I'm hoping this is making some sense. Now, the other big wrinkle in this, and the shapes that are going to come that are not tetrahedral by arrangement are when you have double or triple bonds. Because to get a double bond, you're taking those 4 electrons and you're cramming them into the same space that is normally occupied by 2 electrons. So if you have something like formaldehyde, which has the formula HCO, you have 6 electrons from the oxygen, 4 from the carbon, and 1 from the, H2CO, and 2 from the hydrogen. You have 12 electrons. When you put the carbon in the middle, you bond it to one of the hydrogens and make a single bond to each of the hydrogens, and you make a single bond to the carbon. And then since carbon is more electronegative, you give it all 6 of those electrons. And now you actually have run out of electrons, but carbon has only made 3 bonds. So what has to happen is the oxygen has to donate one of those pairs of electrons to making a double bond. So now you have carbon as the central atom, but it's only bonded to 3 things instead of 4 like in methane, and one of them is a double bond. So we have 3 areas of space occupied with electrons, and the farthest apart they can get is 120 degrees. So we would call this one trigonal planar, and we would say the angle is 120 degrees. And since only 3 areas of space are taken care of, we only need to hybridize 3 orbitals. So we would say it's sp2 hybridized. And again, I'm listening to myself talk, and boy, it's hard. Um, so I'm hoping you're getting this idea that really what you need to know is if I give you one of these things, you should be able to come up with the other ones. Like if I tell you it's trigonal planar, then you should know it's SP2 and it's 120 degrees and that 3 areas of space are taken care of. Or if I tell you it's trigonal planar, then you know it's SP2 and 120 degrees. And again, 3 areas of space are taken up. Now, if I have something like carbon dioxide, CO2, when I put that together, I've got the 12 electrons from the 2 oxygens and the 4 from the carbon. That's 18 electrons. So I put my carbon in the middle, I make a single bond with each of the oxygens, and then I fill the oxygens up because they're more electronegative. And now I've used up all the electrons, all 16 electrons, and carbon only has made 2 single bonds, which is only 4 electrons. So carbon is 4 electrons shy. So each of the oxygens has to form a double bond in order to make the carbon happy, in order to give carbon a full shell. So now, since double bond, the carbon has 2 double bonds, one with each oxygen, and they take up the same amount of space, and they want to be as far away as possible. So 2 areas of space as far away as possible is going to be 180 degrees, and we would say that that chemical CO2 is linear. And so if we only have 2 areas of space occupied with electrons, it's linear, it's 180 degrees, and it's sp hybridized. Okay, those are the big ones, and I want you to sort of think your way through those and see if you can make those connections between the bonding and the shape, the geometry, and the angle and the hybridization. Okay, and I'm going to stop there. There's more to it than this, but let's stop there. Give you a chance to absorb all of that, and then I'll put together another video where I sort of uh, tell you what all of that means as far as the properties goes. That's part of it is now that you know the shape, what does the shape tell you about what the molecule is going to do? All right. Whew. Please give me some feedback on this and let me know how I did.